Hello everyone, welcome back. I hope you have subscribed to my channel. If not, this would be a great time to hit that pause button and just click the subscribe button. I know you love the content I cover. Okay, as we approach the end of 2025, I took the opportunity to look back at the last 3 years and basically to see if we have made any progress in terms of image analysis. While everyone was losing their minds over ChatGPTs and large language models in the last couple of years, some really important stuff actually happened in microscopy image analysis. And in this next 15-20 minutes, I don't know how long it's going to take, I'm going to walk you through the top 5 breakthroughs in my mind from 2022 to 2025. And these examples that you see here on the screen, like SAM segmentation, Cellpose results, and physics-informed diffusion, these aren't just incremental improvements. These are, again, I believe that these are game changers that actually solve real problems that we face every day in microscopy. Okay, so here's what we missed while we were distracted by these chat engines. And of course, in the US, we were suffering through these, or still suffering through, I should say, these research funding cuts. Let's focus on the positive aspects now. Foundation models, the same technology behind ChatGPT made it to microscopy. The denoising got integrated directly into our segmentation pipelines, and diffusion models, the ones that everyone uses for generating AI art, they turned out to be perfect for image restoration. Vision transformers, I love vision transformers. And I love them. I think I started to like them more than CNNs nowadays, more than UNet. They finally proved themselves in our microscopy domain. And of course, in addition, we got new methods that actually handle weird morphologies that traditional algorithms typically fail at, like Stardist, for example. So let's dive into each one. And first up, segment anything for microscopy, or micro-SAM. This is Meta, Facebook's Meta, right? So Meta's SAM model, fine-tuned specifically for our microscopy data. And the key here is that they didn't just take the default model, they actually trained separate specialist model. I can't speak to this morning for some reason. They trained separate specialist models for light microscopy and electron microscopy. And I believe the paper, right there, it got published in Nature Methods 2024. This is the first real foundation model for microscopy segmentation. And again, paper is right here. You can see it. I highly recommend reading it. And here's what I really like about micro-SAM. It combines both interactive and automatic segmentation in one model. You can click a point or draw a box and it segments that object immediately. And of course, we probably are familiar with the original SAM. But in this case, you can do this manually, or you can switch to automatic mode and it finds all instances. And the workflow diagram that you see on the screen here shows how it all fits together. And the cool thing is, from Napari plugin, for interactive segmentation to the automatic annotation to tracking in time-lapse data, we just have one model, multiple use cases. That's absolutely what I love about it. And the performance improvements are also substantial. Look at these numbers. Fine-tuning on microscopy data dramatically improves the segmentation quality here. And the generalist models are trained on diverse data sets covering cells, nuclei, organelles across different modalities. And they actually built in this tracking functionality, which is another huge improvement, especially obviously for time-lapse experiments. So the bottom line here is that this is not just a SAM applied to microscopy, it's actually SAM properly adapted for microscopy. And let's move on to the next development number 2, which is Cellpose 3. with integrated denoising. If you've used Cellpose, obviously if you're a microscopist, especially a life science microscopist, I bet you have used Cellpose. If not, oh man, you're missing out on something. If you work with cells, basically. If you've used that, you know that it's already great for segmentation. But Cellpose 3 adds a built-in image restoration as a processing step. One-click denoising before segmentation. This basically addresses a real problem, right? I mean, microscopy images are they're often noisy, and especially when you're trying to reduce laser power, or when you're trying to image faster with very short dwell times, you end up with noisy images, and Cellpose 3 can really help with those images. And what I appreciate about Cellpose 3's denoising is that it's not trained to restore the original pixel values like you have the traditional denoisers. Instead, it's actually trained to output images that segment well. I hope that makes sense. They use to do that, they actually use a combination of perceptual loss and segmentation loss. So look at the diagram here on this slide. The denoising network learns to produce images that the segmentation network can handle. Okay, so this task-specific approach works, I think, works better than generic denoising methods. Okay, and it also handles 3 types of degraded microscopy images. One, in fact, they're addressing all the challenges in microscopy here, right? I mean, noisy images from low laser power, blurry images from obviously your out of focus acquisition, and undersampled images from, let's say, faster acquisitions. And these examples show nuclei at different laser powers, high power on the top right here, low power in the middle, and Cellpose 3 denoised on the bottom. And the performance curves also show that it consistently outperforms other denoising methods. So this is really practical. It means less phototoxicity, longer time lapses, faster imaging. So it really addresses microscopy challenges that we actually face. So I want to, before moving on to the next, development, just want to end this by saying there are 3 key points here. It solves real-world imaging constraints, like we already saw. It generalizes to data never seen during training. So these test images are completely new. And the key thing is that it doesn't hallucinate structures. You probably heard of large language models, hallucinate and all that. They actually validated this quantitatively by checking false positive rates. And look at the comparison across different cell types and modalities. The super generalist model works remarkably well out of the box. I mean, the Cellpose 3. Okay, now let's move on to the next development number 3 here, which is diffusion models for microscopy restoration. These are denoising diffusion probabilistic models, DDPM, denoising diffusion probabilistic models, applied to microscopy domain. You condition the model on a low resolution or a noisy input, and it predicts the high resolution version, basically. And there are 2 key papers here that I'm showing on the screen. One is by Osuna Vargas. I'm hoping I'm saying that name right, on the general restoration itself. And another one on the top here by Lee on physics-informed diffusion. And they both are from 2024, so very recent developments actually. The physics-informed approach is what I find especially interesting, because instead of just learning from the data itself, they actually incorporate the actual physics of light propagation into the loss function. That's amazing. So this diagram shows wide field microscopy, confocal, and how they simulate the imaging process. And by including the point spread function and the noise model, they avoid the hallucinations actually that pure, like actual clean, pure deep learning methods can actually produce. The model understands the physical constraints of microscopy, which is kind of great. I'm sometimes amazed at how people think, especially the physics informed models is what I'm kind of fascinated with quite a bit, not just in microscopy field in general, but in microscopy, this absolutely makes sense. So I definitely recommend reading these papers. And another advantage of diffusion models is that they're probabilistic. So you can generate multiple predictions from the same input and average them for a higher signal to noise ratio. Isn't that cool? You also get uncertainty quantification. So the model tells you where it's confident and where it's actually guessing. And these examples here show STED microscopy of mitochondria, and look at the metrics. DDPM and especially the DDPM average outperform all the traditional methods. And here, there's a concrete example on super resolution data starting from wide field. You can see the progression through unit DDPM and physics informed DDPM, and of course at the end you have DStorm. And the physics informed version actually gets closest to the ground truth. Compare this across different biological structures, the improvement is very consistent here. So of course, this enables imaging with lower laser doses, right? While maintaining your image quality. Vision transformers, now let's, transformers itself is like a buzzword nowadays, and vision transformers got started with, working with images using the transformer technology. And basically these are attention-based architectures, right? That actually replace or in some cases augment the traditional convolutional neural networks. And they do multi-scale feature extraction. And if you have time to read only 3 papers or 3 technologies that you want to dive deeper into, then I recommend the SWIN Unit R with hierarchical transformers, Unit R with pure transformer encoders, and SegFormer 3D for efficient 3D segmentation. So I really bookmark these 3. I tend to forget things if I don't keep up all the time. So I bookmark them so I can just at least read them once a month or once every 2 months to keep my memory fresh. So I find them to be that useful and important. And these models use attention mechanisms instead of just convolutions. The hierarchical design is very important. You process features at multiple scales. That's why the hierarchical design is, I believe, is key. SegFormer 3D is actually, I find it to be particularly, clever, I think, for lack of a better term, because it extracts multi-scale volumetric features using a 4-stage hierarchical transformer, and then it uses all MLP decoder. Well, so who cares? This makes it efficient enough for 3D medical and microscopy data. So if you're working with 3D, in general 3D data, I would say microscopy data, please give SegFormer 3D a try. And also, why are transformers good, right? For ChatGPTs and large language models, why are we using transformers? Because of this long range understanding of the scenario. So vision transformers capture this long range dependencies through self-attention. And why is that important? Again, it gives global context that pure convolutional neural networks or CNNs actually miss. And these vision transformers are obviously, by nature, they're good for large connected structures. So, of course, I always, try to use convolutional neural networks like UNet, for example. But sometimes the data is a bit complex, and especially if you're working with 3D, then vision transformers, I definitely recommend giving that a try. So these cardiac MRI examples show ground truth versus different transformer architectures. And the segmentation quality, as you can see, is comparable across all these methods, basically proving that transformers can either match or in many cases exceed the convolutional neural networks. And the hierarchical designs are what makes these transformers, again, practical for microscopy. And I think I find myself repeating this hierarchical design aspect because that is really very important when it comes to microscopy. Right? You're not just doing image classification. You're not just saying, hey, you have a large image, convert that into multiple patches of, I don't know, 256 by 256, and each patch go ahead and vectorize it in one dimension, obviously, and then go ahead and feed it to transformers and all that, blah blah blah. That's fine. That actually works very well if you want to classify the image, the entire image, saying, oh, there is a horse in this image, there is a monkey in this image, or whatever. No, for microscopy applications, medical image applications, you going down to pixel level is very important. Really, going down to pixel level, like what do you have, like is this mitochondria and is this different organelles and so on. It's very important. So you cannot just go down to pixel level and embed and create embeddings for every pixel. That creates like millions of embeddings, and transformers don't work well with that type of embedding. Sorry for going technical here, but I hope that makes sense to some of you. Right? So that's why hierarchical designs are invented in this case that make actually these transformers practical for microscopy applications. And the shifted window attention, like the SWIN approach, again, the SWIN unit R, the SWIN SW, actually, the SWIN actually stands for shifted windows, by the way, I should have mentioned. This approach, they only compute attention with local windows and then shifts them. Again, you need to be clever in terms of how to properly, design your model architecture, so you're not just creating embeddings at every pixel level. At the same time, you're not losing context down to the pixel level, right? So SWIN approach actually addresses that. And the diagram shows 3D tokens divided into windows here, and multi-scale pyramid features capture both the fine details and, of course, also the global structure. So that's a neat innovation, I believe. And I should also mention it's efficient enough for high resolution volumes, which of course is important for microscopy data. This comparison shows unit R against other methods on brain tumor segmentation, and look at the different color regions. Obviously, they represent different tumor components, and unit R actually captures fine-grained details here, while at the same time maintaining the overall structure, right? So it's capturing these fine-grained details, and the transformer architecture gives you both. In general, the transformer architecture compared to traditional CNN architecture gives you both the local precision and global context. I find myself like repeating this hierarchical, local, global. It's super important for microscopy. That's why I hope at least if I repeat it 7 times, maybe I'm effectively communicating at least once, between these 7 variations. So I apologize if you find that I'm beating this horse here. So anyway, moving on to the next one. I think we talked enough about transformers. Moving on to the next development 5, Omnipose. Sounds like Cellpose, right? Omnipose for complex morphologies. Of course, it sounds like Cellpose because this is built on the Cellpose framework, but uses a completely new flow field approach. Which means instead of computing flow towards the cell centers like Cellpose does, Omnipose uses the distance field gradients. Again, please read this paper published in Nature Methods 2022 if you want to dive deep into this, but it's specifically designed in this paper, at least, for bacterial segmentation because they have all these wonky weird shapes, but in general it should work quite broadly, not just for bacterial segmentation. And here's why I think Omnipose kind of shines. It's truly morphology independent, and it works on, of course, like bacterial, it works on elongated cells, these branched cells, and any irregular shapes, anything basically. Not that I tested this on anything. I tested this on like these weird wonky shapes, and it seems to do a pretty good job. And unlike Stardust and methods like that, there is no assumption about star convex shape. right? I mean, when you use stardust, it assumes that your shape is star convex. In other words, what it means is if you sit at some center of this region, you should be able to see every part of the cell walls. That's probably the easiest way to explain that. In this case, there is no rule like that. This figure here shows the distance field approach, and where you compute the gradient of the distance field, which points towards the boundaries, and it doesn't matter what the cell shape is. And the flow fields look completely different from Cellpose, especially for these bacterial cells here. And Omnipose has a direct 3D extension. Not, I believe like Cellpose, even Cellpose 3D actually does a slice by slice, but in this case, it's a true 3D flow field. Yeah, and these 3D images here show the difference. The segmentation results here demonstrate that, of course, the native 3D processing handles these complex 3D morphologies better. The graph is a bit small, but I hope you can see. Again, please read the paper. And in this case, the graph shows Omnipose outperforms Cellpose on these. I believe these are plant data sets that you see on the screen. So, in summary, if you have 3D microscopy data with complex shapes, I think this is the method to use. Okay, let's summarize everything before I end this video. I didn't expect this to go, I don't know, probably it feels like about 20 minutes or so since I started talking. I just wanted to flash some screens over there and end this video, but as usual, I guess I talk too much. But I hope you find this to be useful and educational. Let's end with the final summary of all these 5 methods. MicroSAM is your general purpose foundation model. Use it for interactive annotation, and of course it works across multiple modalities. Cellpose 3 is where you have noisy or degraded images. DDPMs for physics-informed restoration and super resolution. Vision transformers, my personal favorite, for large structures and 3D volumes. And of course, Omnipose for like bacteria or filaments or anything that has weird morphology. Yeah, different tools for different problems. Now, I should mention the practical implementations, because these are not like, I mean, at the end of the day, what does this mean to you as a microscopist? Well, you can work at if you have to work at lower laser power, that means obviously less phototoxicity. Both Cellpose 3 and DDPMs enable you to work with that data. Faster annotation with these foundation models like MicroSAM can help you save a lot of manual work, obviously by speeding up your annotations. And better handling of, I try not to use weird quite often, but again, weird or let's use the term challenging morphologies with Omnipose basically means you can actually segment data that was obviously previously impossible. Like previously you used to do manual segmentation, but with these type of challenging morphologies, you may find Omnipose to be, pretty effective. And improved 3D segmentation, both from transformers and Omnipose, makes your volumetric analysis practical. And I should mention, these are not just academic improvements. These are not like just, okay, let's publish a paper. These are not just academic improvements. They solve real microscopy problems. Okay, I think I should end now. So that's it. These are the 5 major I can't even speak anymore. These are the 5 major breakthroughs in microscopy image analysis from 2022 in the last 3 years. And all of these have working Python implementation you can use today. You don't have to code anything from scratch, right? So please do let me know in the comments if you want me to do hands-on tutorials. I didn't plan on doing that, but if enough of you request, I consider doing hands-on tutorials on each of these methods using real data sets. And thank you guys again very much for sticking for 20 to 25 minutes or so. And thank you very much for watching.